Hello everyone, greetings of the day. We are Group 10 and I am Parash Joshi, joined by Krishna Subedi and Rajesh Dhakal. In this video, we'll be showing you how we use machine learning for our assessment to predict the compressive strength of concrete using various AI-based models. The presentation is divided into different subtopics, including introduction, data preparation, algorithms, and model section, final model performance estimates, and conclusion. Starting with the introduction part, concrete, as we all know, it is the backbone of our modern infrastructures from skyscrapers to bridges and highway. As we all know, concrete is a topic that is of utmost importance in the field of engineering and construction. The overall performance of the structure depends upon the quality of the concrete, and the quality of concrete is determined by its compressive strength, which is traditionally measured using a conventional crushing test on a concrete cylinder in a lab, and this test generally takes 28 days to get the results, which is a very long period of time. Hence, the main aim here is to provide the insights to how we can use machine learning algorithms and train them to predict the concrete compressive strength with accuracy and efficiency in order to reduce the time taken to determine the concrete strength. In this presentation, we will be discussing about the datasets, techniques, and evaluation metrics we employed, shedding light on the practical application and implications of our work. The very first step in the machine learning is data preprocessing, which is basically a crucial step in the data analysis and machine learning pipeline. It involves a series of operations and transformations that are applied to raw data to make it suitable for the analysis. So the datasets were obtained from Kaggle, and it is about the concrete compressive strength, and the data characteristics is the actual compressive strength for a given mixture under a specific age, which was determined from the laboratory is taken. And for the data characteristic, we will choose a target prediction and eliminate rows with null data. Similarly, we'll separate into testing and training values, and where generally the testing size will be 30%. The steps includes data cleaning, data transformation, data reduction, handling imbalanced data visualization, and handling duplicates. So these are the things that we did for the data pre-processing. We will be using the data sets obtained from the Kaggle. The dataset includes different parameters such as cement content, blast furnace slag content, fly ash content, water content, super plasticizer content, etc., and the actual compressive strength, which is given in MPa for a given mixture under a specific age, which is determined from the laboratory. And as we know, data pre-processing includes various steps such as data cleaning, data transformation, data reduction, handling imbalanced data splitting, feature scaling, etc. These are the steps that we have done in the data pre-processing. Here we can see various parameters of our dataset, and similarly here we can see different parameters of our dataset and the weightage of those ingredients in determining the concrete compressive strength. So from data pre-processing, we can confirm the columns have correct data type. Similarly, we have to check for if there are any null values or any duplicated values. Similarly, we can also see that different ingredients which have or may not be mandatory to be included in the mixture to get the concrete compressive strength. For example, in our case, from this table we can see that the ingredients like fly ash, super plasticizers, blast furnace slag are not mandatory to compose a concrete mixture, which is actually true. In data analysis and machine learning, calculating the correlation among input variables is a common practice to understand how different features or variables in our data sets are related to each other. So basically here we can see calculation of the correlation and developing a heat map. From the heat map, we can predict the correlation between the input variables. For example, from the graph we can see that the cement is the best predictor as it shows a strong correlation. Similarly, water shows a negative correlation with the concrete compressive strength, and super plasticizer and fly ash shows a strong correlation, followed by blast furnace slag and fly ash being a very weak predictors. Now the other part of this presentation will be explained by Rajesh Dhagal.
Hi, it's me Rajesh Takal, and for this project we have used four different types of algorithm, in which they are random forest method, decision tree method, naive Bayes method, and deep learning methods. And in this chapter we will compare the results of the models. And talking about the random forest regression, it is a type of regression in which it is generally used for predicting continuous target variables such as numerical output, just like compressive strength of concrete that we have been using in this project. And we have provided information about features and its importance, indicating which predictor variables have most significant impact on the target variable. Performance measure on the basis of the following two categories. First is mean square error method, and second is mean absolute error method. And in addition, we have a regression and classifier type of model. As we know, a regression type of model is used in continuous data set, while a classifier are used to predict result on classification. Since our data set is continuous, we will focus on regression type of modeling, and as part of our assessment requirement, we will add more features to the existing data set in order to imply this classifier model. And the random forest classifier method is that which combines multiple prediction from models and makes more accurate and robust prediction, and it's able to handle complex data set. Its concrete strength depends upon various parameters, and individual trees can be trained independently, and allows to predict features having most impact on classification decisions. In the right side, you can see the accuracy, precision, and recall of this classifier model. Uh, and the third one is decision tree classifier. Generally uses its usage decision tree as a predictive model for classification tasks, and it handles both categorical and numerical data. And in the figure below, we can see its accuracy level, precision, recall, and all the flow chart. The next one is knife-based classifiers method, and it's commonly used for classification tasks. It is simple, speed, and effectiveness on high-dimensional data. Knife-based classifiers are often a good starting point for classification tasks and can serve as a baseline model for the comparison. In this project, we can see all the accuracy, precision, and recall of the night-based classification scores. And thank you. And now my friend Krishna Subedi will continue the rest slide.
Hi, this is Krishna Subedi. Let's explore deep learning, a fascinating aspect of AI that uses synthetic neural network to model how our brain functions. A multilayer perceptron (MLP) is one of the types we are discussing. It resembles a layered network of nodes inspired by the brain that processes data and recognizes intricate patterns. To change how effectively the model functions, we can change the factors like layers, neurons, and activation strategies. However, keeping in mind that training an MLP requires data with distinct labels. It gains knowledge from these labels, modifies its setting to produce more precise predictions. In order to compare how well various machine learning models perform, like random forest RF classifiers, decision tree classifiers, naive Bayes, and multi-layer perceptron (MLP) classifiers, we need to test them on the same dataset using the right evaluation measures. Typical measures include accuracy, precision, recall, and F1 score. It's important to note that for the tasks like predicting continuous values regression, we need to use the matrices such as mean square error, root mean square error, mean absolute error, and R squared. Now, for the random forest classifier, we see high scores in accuracy, precision, recall, and F1 score. The decision tree classifier consistently performs well at different depths, slightly lower than the random forest. Naive Bayes classifiers show varying performance based on the smoothing parameter. However, values like 1 lead to lower performance, while the lower values 0.5 and 0.25 result in improved accuracy. precision and recall, and F1 score. In multilayer perceptron MLP, we have three configurations. The one with two hidden layers and threshold to perform the best, with high score in the accuracy, precision, recall, and F1 score. The model with one hidden layer shows lower performance, and the model with zero hidden layers, perceptron, has the lowest performance. In this comparison of model accuracies, we have observed distinct performances among the four machine learning models evaluated. The random forest classifier has emerged as the top performer in the terms of overall performances across various thresholds. Its high accuracy and robustness make it a standard choice for predictive modeling. Following closely is a decision tree classifier showcasing consistent and commendable performance across different depths. Although slightly lower than the random forest, it remains a reliable option. On the other hand, naive Bayes classifier and multilayer perceptron MLP demonstrate variability in performance influenced by the respective hyperparameters. The naive Bayes classifier shows sensitivity to the smoothing parameter, affecting accuracy, precision, recall, and F1 score. For the MLP, the number of hidden layers and the threshold greatly impact its performance. The selection of most suitable model ultimately hinges on specific requirements of the task at hand and the trade-off between the various evaluation matrices. Factors such as interpretability, computational resources, and the relative importance of precision, recall, and accuracy in the context of problem must be carefully considered. It's essential to acknowledge the real-world variability in compressive strength, notably affected by the water-cement ratio. While the models provide theoretical predictions, uh, practical outcomes may deviate if the actual ratio in real-world application does not align precisely with the predicted ratio used in the training and testing. This underscores the importance of real-world validation and continuous model refinement to ensure reliable performance in practical setting. Before we finish, let's say a big thank you to the following references who have helped us along the way. Thank you very much.